Good morning. My name's TYudd, and for my final project for Predictive Analytics 7332, I explored a data set from Kaggle, which was sourced from the National Institute of Diabetes and Digestive Kidney Diseases, looking at the Pima Native American tribe in central Arizona, specifically looking at women and their medical histories and whether or not they have diabetes. So the objective for my project is to utilize this raw data set and employ our predictive analytics techniques of logistic regression, all of the tree-based models, and neural networks in order to generate a predictive model on whether or not these specific women, this group of women, will have diabetes or not. So to give a little bit of background about this data set, the 7 fields that were used were pregnancies, glucose level, which is blood sugar, the blood pressure, skin thickness, insulin, if applicable, body mass index, diabetes pedigree function, which is a ratio based on the family history of that patient, and then their age in years. And lastly, there was outcome, which is a binary 0 and 1 field. This originally is an integer in the data set. So before I jump into logistic regression, I convert it to a factor so that it works for the model. But before doing anything, I had to do a little bit of data cleanup, starting with converting zeros where they truly didn't make any sense, such as the glucose or blood pressure. Somebody's blood pressure can't be 0 if they're living. So I knew that that wasn't intentional. That was just an omission in the data. So I converted those zeros to the column mean for those respective fields. There were no NAs or errors in the data. So that was the only part of the data cleanup that I had to do before I started. Logistic regression is the first predictive analytics technique that I use. But before I did that, I did some background data exploration, starting with a box plot, comparing the patient's glucose levels against whether or not they were diagnosed with diabetes. So you can see the blue box are the positive diabetics, and they, on average, have higher glucose levels, which makes intuitive sense. And then at the bottom, usually there's some outliers for people who have very high glucose levels, but didn't end up getting diagnosed with diabetes. So then to dig into this a little bit further, I ran a 2-sample t-test on the difference of means for the people with and without diabetes. This was difference of means in their glucose levels. And it returned a very low p-value, indicating that there is a statistically significant difference between the average glucose of somebody with diabetes and without diabetes. The last thing that I did before I actually ran the logistic regression model was observed the proportion in the raw data of who had and who didn't have diabetes. So 35% were diagnosed and 65% were not, making 65% our baseline accuracy. So once I moved into the actual running of the logistic regression model, I started with all of the fields in my initial model here to see what was statistically significant. After doing that, I saw that the only actual predictors that were significant at the 0.05 alpha level were pregnancies, glucose, and BMI. So I ran the model only using the significant predictors. And then I have my interpretation down here. I hid the actual output because it was way more lines, but the actual coefficients for this model were pregnancies 0.1497, which meant that for every 1 unit increase in the number of pregnancies that that patient had, the logarithmic odds of that patient having diabetes increases by 0.1497. For glucose was much smaller, 0.04, basically, saying that for every 1 unit increase in the patient's glucose level, their logarithmic odds of having diabetes increases by 0.04. And then BMI was in between. So for every 1 unit increase in the patient's body mass index, their logarithmic odds of having diabetes increased by 0.11. The overall accuracy of this model was 74.5%, which was better than that benchmark accuracy we saw of 65%. The true positive rate was 52.8, and the true negative rate was 86%, which is the sensitivity, which was much higher than the specificity. I'm going to compile all of the models at the end, so I'm going to go right in now to the classification tree. Starting with the diagram, you can see here that the way the output shows is that if a patient's glucose is greater than 127, then it moves on to the criteria of body mass index. From here, if their body mass index is less than 29.9, less than or equal to 29.9, then the model is going to classify them as a no for having diabetes. Whereas if it was greater than 29.9, it would go back to evaluating glucose as like a secondary criteria. And if it was greater than 154, then the model would classify them as a one, so having diabetes. The same logic applies for the people at the original node who had less than or equal 100 to 127 as their glucose level. Pregnancies is evaluated next. Depending on the pregnancies, they evaluate the age, BMI, before getting to those final nodes that determine whether the model would classify them as a zero, not having diabetes, or a one, having diabetes. So looking at the performance of the classification tree, which is our first tree model, the overall accuracy was 0.725, which is a little bit lower than the logistic regression. However, it did have a better true positive detection or the sensitivity, which was 0.6415. Additionally, I had to condense some of the rows to fit them in the 5-page R Markdown report, but I did test what the five most important or the three most important predictors were based on their mean decrease in the Gini index, and they were um, glucose, BMI, and age, which is slightly different from the statistically significant factors we found in the logistic regression, which were pregnancies, glucose, and BMI. So BMI and glucose have made it in two of the models so far, but pregnancies dropped off. So the second tree model that we did was the random forest. So I had already partitioned the data previously, so I've hidden those outputs. But you'll see here with the error rate for the zeros and ones, the diabetic group had the higher error, while the non-diabetic group had the lowest error, and they did not converge at all, with the out of bag error being in the middle at 22.93%. For random forest, I also checked what the most important variables were, and it was the same as the classification tree, where glucose, BMI, and age were the top predictors. Lastly, for the tree analysis, we did the random forest with bagging model, which had the highest overall accuracy at 75.16 and the highest specificity at 86. So it was better at detecting the true negatives. The error rate here, the error chart here was very similar to the random forest, where the diabetic group had the higher number of errors, whereas the non-diagnosed group had lower, and out of bag was in the middle, this time at 24.72, so a little bit higher than the random forest. The next model that I explored were neural networks. So I started by converting the factors that we had previously been using back into integers and then normalizing the data for the model. I had to then partition this new data set into the 80-20 split. And I started by using one hidden layer, using those top three predictors that we had found previously, the glucose, BMI, and the age. After doing such, I've hidden the output because the return alone was 5 or 6 pages, but the overall accuracy was 74.5, with the fifth repetition being the one with the lowest error. So that's what I used here in my plot. The error was 289.5, whereas in the other repetitions, it was in the 290s. To wrap it all up, I did a comparison of all of the models that we did showing that the random forest model had the highest accuracy at 75.2%, while the classification tree model had the highest sensitivity. In second place for the accuracy, logistic, random forest bagging, and neural network all had 0.745, so they were very similar. My final recommendation was that the hospital system in central Arizona that serves this Pima Indian population should use the random forest model as their starting point to develop a more sophisticated predictive model so that the patients who come in, when they get their blood pressure, their skin thickness, and their glucose, are able to have an accurate assumption on whether or not they're going to be diagnosed with diabetes in the future so that they can start focusing on preventative care. Lastly, in my detailed R code, I did explore clustering analysis, both k-means and HCA. However, the model was very poor, and the average silhouette width was only zero point 0.2, with a lot of negative values. So I felt that the random forest and these tree-based models were much more accurate and more worthwhile to include in this report. However, I did want to mention that I do have that in the detailed R code that supports this report. Thank you for your time and a great semester.